Mathematical Induction Part 2. In Part 1, we dealt with proving divisibility and proving that one expression is greater than or greater than or equal to another expression. So now we're going to go on to prove rules related to sequences or series and depending on the natural numbers 1, 2, 3 onwards. Have a look at this pattern. One odd number, 1 squared. Two odd numbers added, 4, 2 squared. 3 added, 3 squared. 4 added, 4 squared. So it seems that the sum of the first n odd numbers is n squared. Well, it's true for n equal to 4. What is true for n equal to 5? Well, write it and see. You see, the problem is we cannot use special cases to prove anything in maths. This is a very simple case, but it becomes far more complex later. So we need to start with the simple cases. So we need something more rigorous. Doesn't mean it's true for n element of natural numbers yet. Have a look. That's what we're going to be trying to prove. Twice 1 minus 1, twice 2 minus 1, twice 3 minus 1, twice 4 minus 1, therefore twice n minus 1. Now that's not part of the proof, that's just showing the pattern, and there's the general formula, the general term. I'm sure you know how to find the general term of a mathematical sequence or series, and n squared being the square of the number of terms. So that's what we're going to try to prove. By induction, ladder principle, we're going to go to the first rung, prove that we can go to the first rung, and then prove that once we're on a rung, we could get on to the next rung. So, for n equals 1, we're going to take just the first term, because that's all that means on the left, term 1. And we're going to end up with left-hand side equals 1. Right-hand side, we substitute into the formula 1, and we get 1, which is the same as the left-hand side. So true for n equals 1. Now we're going to try to prove it that once you're on a rung, you can get to the next rung. So let's assume that we're on some rung, let's call it the kth rung. So assume true for n equal to k. Remember, we're allowed to do it because it is true for at least one value. Permission granted. Yippee. Therefore, this is the case. Because it's true for n equal to k, we have that up to k terms. Now, what we're going to do is we're going to add the next term onto the left-hand side, which is pretty straightforward. All we're going to do is put k plus 1 instead of k, and n, and we're going to put it there. K plus 1 instead of n, or k plus 1 instead of k, but we're going to put it in there. We're going to leave these and add the next term. And if we add something to the left, we must add the same thing to the right. There we are. Notice, this comes down, moves across, because none of this changes. That doesn't change. We still have the same equation. Have a look. There's the left-hand side there. There's the right-hand side there. All we've done is added in an extra term. And we're allowed to do that to an equation as long as we do the same to both sides. And notice k plus 1th term, because I have k plus 1 instead of n, 2n minus 1, so therefore 2k plus 1 minus 1. Notice that. Now we have k plus 1 terms on the left. We're going to try to prove that that right-hand side simplifies down to k plus 1 squared. 2k, k squared plus 2k plus 1. Because then we'll have the formula k plus 1 all squared, which means it's adjusted to a new formula. To do that, we're going to multiply it out, and we should see that it should refactorize. We'll just hope so anyway. There we are. Oh, look, there we are. K plus 1 squared. That's exactly what we're needing showed equal to. Pretty straightforward, this one. So therefore it's proven that if you add the k plus 1th term, you going to end up with the k plus 1 formula. True for n equals 1. True for n equal to k means true for n equal to k plus 1. Therefore, true for all n elements of natural numbers by mathematical induction. Let's do another example. First rung, n equals 1. Left-hand side, the first term. Right-hand side, substitute 1 for n. And we get 1 equal to the left-hand side. True for n equals 1. Now we're going to get on to some rung. We'll call it the kth rung. So we're going to say, assume true for n equals k. Now we're going to prove that once there, you can get to the next rung. We're going to prove that true for n equals k means that if we take an extra term, k plus 1th term, add the same on to that side, that formula is going to adjust to a k plus 1th formula. K plus 1th term to both sides. Well, there we are. There's the term, so therefore 3 times k plus 1 minus 2. 3 times k plus 1 minus 2. Notice once again that there it is. We haven't taken anything out. We haven't replaced anything. I've added a new term. And I've added the same to the right-hand side. There's the right-hand side, and I've added the same to it. Let's go to our rough work. Yes, get a move on. Right, now there we are. Here we are. Now, we say, well, what do we want to end up with? What must this end up as being? Well, we want a k plus 1th formula. There's the nth formula. There's the kth formula. We want a k plus 1th formula, which means putting k plus 1 instead of n. There we are. K plus 1, 3 times k plus 1 squared minus k plus 1 all over 2. Now this is where we got to get a bit clever here. What we're going to do is simplify this. There we are. So please, this must end up as being this. If we find a common denominator and simplify, hopefully it's going to end up as this. Maybe it'll end up as something higher up, and we can then pick it up immediately. Let's just see. Common denominator. Oh, yippee, I'll see why in a moment. 3k squared minus k. Put this over 2, so that becomes 6 into k plus 1. 6k plus 6 minus 4. There we are. Now, I'm saying yippee straight away, because have a look here. 3k squared minus k plus 6k minus k plus 6k. 6 minus 4, which is 2. 3 minus 1 is 2. So I have the right thing. So I'm going to go from there to there. Just slight readjustment. How did I know to do that? Because I have it here. And I'm going to go from there up that way to there. That rough work is so useful. What do we have now? We have the k plus 1 instead of k. There it is there. Another tick. True for n equals 1. N equals k true means n equals k plus 1 true. By math induction, true for all n element of natural numbers. There is now a third video which now just goes through more examples for you, and you can follow them and try them yourself.